This is Math 120, Chapter 3, Systems of Equations. The first 4 sections of Chapter 3 deal with systems of equations in 2 variables, and then the last 3 sections will be about systems of equations in more than 2 variables. So it begins with a simple objective here to find the solution of systems of equations in 2 variables by graphing, and to determine whether a system is consistent or inconsistent, and whether the equations in the system are dependent or independent. So that's the objective of section 3.1. And so let's begin by learning how to solve systems of equations graphically. That'll be the first step. So here's exercise number 1. We are given 2 equations. Solve each system graphically. That's number 1 in the second exercise in just a moment. And so one equation says minus 2x plus y equals 1. And the other equation is 3x plus y equals 1. When you look at the first equation, what we can do is we can rewrite it as we add 2x to both sides. So then the first equation becomes y equals 2x plus 1. And in the second equation, when we subtract 3x on both sides, we get y equals minus 3x plus 1. Next, we will graph these 2 equations. And now, of course, in slope-intercept form. The first equation has slope 2 and the y-intercept of 0, 1. And the second equation has a slope of negative 3 and the y-intercept is also 0, 1. So let's graph these 2 equations. It doesn't really matter which method we are using for that. So here you see the 2 graphs of the equations. Here's the graph of y equals 2x plus 1. And here's y equals minus 3x plus 1. And they intersect in the point on the y-axis 0, 1. So the point of intersection is 0, 1. And that is the solution set to this system of equations. Now, we can verify that this is true by substituting for x the value 0 and for y the value 1 in the original equations. So for the first equation, then we have minus 2 times 0 plus y, which is equal to 1, and that is equal to 1. So that checks. And for the second equation, we have 3 times 0 plus y, which is 1, and it also equals 1. So this solution works for the second equation as well, so we can be confident that this is the solution to this set of equations. And example number 2 will be very similar. So here we have the equations already in point slope form. Y equals 1/2 x and y equals minus 1/4 x plus 3/2. So let's graph these 2 equations. And again, by now you know how to do this, so I won't explain that. You'll just see them in a moment here, how they look on the xy coordinate system. Graphing these 2 lines, y equals 1/2 x and y equals minus 1/4 x plus 3/2. They intersect in the point 2, 1. So the solution would be the ordered pair 2, 1. In other words, x equals 2, y equals 1 would be the solution to the system of equations. And again, I leave it up to you to verify that this is correct by substituting the values for x and y into these equations and to confirm that this indeed is the solution to this system of equations. You don't always have to do it. You don't have to verify that that's really the solution. But I would recommend you make it a habit. Just to get in the habit of doing it, it's a good idea. You may remember that when we solved one equation, one variable, let's say 3x plus 2 equals 14. So in this case, we subtract 2 on both sides, so 3x equals 12. And then we divide both sides by 3, so x equals 4. So here we have one solution. Okay, you may remember that. Now, it can also happen that the equations with no solutions. For example, the equation x plus 1 equals x plus 3. When we subtract x on both sides, then we wind up on the left side with 1 and on the right side with 3, and that of course is a false statement, and that means there's no solution. So no solution in a case like this. And a third case that may occur when you have an equation, one variable, for example, the equation x plus x equals 2x. So if we simplify the left side, it would be 2x, that equals 2x. And so any real number would work as a solution. So there are infinitely many solutions. Infinitely many solutions. Or we can say the set of real numbers is a solution set. And we will encounter something similar when we're having systems of equations. So that's what the next example is about. Before we talk about consistent systems and inconsistent systems, let's solve exercise number 3. Solve graphically. Y plus 2x equals 3 and y plus 2x equals negative 4. So let's graph these two equations. So when we graph the two equations, the lines appear to be parallel, and rewriting the two equations in slope-intercept form, y equals minus 2x minus 4 and y equals minus 2x plus 3, we notice that they have the same slope. In other words, that confirms that the lines are parallel, and of course parallel lines don't intersect. Therefore, in this case, there is no solution. So when we have parallel lines, there is no solution. And so let's look at the consistent system and inconsistent system. If a system of equations has at least one solution, then it is consistent. A system of equations that has no solution, if a system of equations has no solution, then it is inconsistent. So here we have an inconsistent system because there's no solution. So let's look at example number 4. Classify each of the systems. In margin exercise 1-3, it's consistent or inconsistent. So remember, example number 1 had one solution, so it is consistent. Consistent. If you go back to exercise number 2, the margin exercise number 2, it had one solution, and so it's consistent also. And then the one we just did, number 3, exercise number 3, had no solution. Therefore, it is inconsistent. Inconsistent. Next, let us solve graphically the system of equations 2x minus 5y equals 10 and minus 6x plus 15y equals negative 30. So let's graph these two equations. Let us solve each equation for y. So we subtract 2x on both sides. We have minus 5y equals minus 2x plus 10. We divide by negative 5, so y is equal to 2/5 x minus 2. So that's rewriting or solving the first equation for y. Now let's solve the second equation for y. So we add 6x to both sides. So we get 15y equals 6x minus 30. And now we divide both sides by 15. So y equals 6/15x, and minus 30 divided by 15 is negative 2. And so we can simplify 6/15 to 2/5 x minus 2. So we notice that by solving both equations for y, we discover they are really the same equation. In other words, the graph, there will be only one graph, one line. So let's graph that equation. If for a system of two equations and two variables, the graphs of the equations are the same line, then the equations are dependent. And that's what's happening here. When we solve the equation for y in each case, we get the same equation, so they are represented by the same line. If the graphs of the equations are different lines, then the equations are independent. So in other words, here we have a dependent system. And that has infinitely many solutions. In other words, for one line, we pick an x, we get a corresponding y, and there are infinitely many solutions. So here we have infinitely many solutions in this case. So let's look at a summary of all of this. When we graph a system of two equations, one of the following three situations can occur. And that is when the two lines intersect, the graphs intersect, then the system is consistent, and the equations are independent. So one solution. The other case is where the lines are parallel, the graphs are parallel, and then the system is inconsistent, and the equations are independent. And the last case that we just did, when you have infinitely many solutions, the equations have the same graph, and the system is consistent, and the equations are dependent. Okay? So let's think about why it's called a dependent system. So exercise number 5, we said, was a dependent system. How so? Well, if you look at the first equation, by multiplying the first equation by a factor of -3, so we have -3 times 2x minus 5y equals 10. Then we get minus 3 times 2x is minus 6x. And minus 3 times minus 5 is positive 15y. And minus 3 times 10 is minus 30. So that'll give us a second equation. In other words, the factor, the linear factor of minus 3 establishes the fact that that the second equation depends on the first equation or vice versa. That's why it's called a dependent system. It's a linear factor of minus 3 in this case. So let's look at the guided solution exercise here. In margin exercise 1, the graphs are different, so the equations are independent. In the margin exercise 2, the graphs are different, so again the equations are independent. If you go back, and then exercise number 3, the graphs are different, so the equations are independent. independent. And then the last one, number 5, where the two graphs were the same actually, so the equations are dependent. And I showed you they were dependent on each other by a factor of -3. So here are then other cases, similar to what I showed you with one equation, one variable. So the number of solutions in example number 1, we had a system that's consistent, and the graphs of the equations are different, so the equations are independent. Then example number 2, where the lines are parallel, the system is inconsistent, and the lines are different, so the equations are independent. And then the last one, the infinitely many solutions, the system is consistent, but the equations are dependent. Okay. Now, solving equation system of equations graphically is a good idea in many cases, but there are also disadvantages, and we'll talk about that in more detail in a moment. But if we solve them algebraically, here just having one equation, one variable, the way they want to do this, I'm going to show you in a moment how that works. There are disadvantages and advantages to either way, doing it algebraically and doing it graphically. So when we solve 7a algebraically, x plus 1 equals 2/3 x. We subtract 2/3 x on both sides, so then we have 1/3 x plus 1 equals 0, and so we subtract 1 on both sides, so then x is equal to -3. That would be the algebraic solution. Okay. Very straightforward, nothing to it. For the b part, we let f of x equal to the left side, x plus 1, and then let's say g of x is equal to the right side, 2/3 x, and then we graph each of these functions. So when we graph these two functions on the same set of coordinate axes, f of x equals x plus 1 and g of x equals 2/3 x, we find that they intersect at the point x equals -3. So, of course, we have the same solution. Section 3.2 is solving systems of equations for substitution. Solving by graphing, though useful in many applied situations, is not always fast or accurate in cases where solutions are not integers. So when we have fractions, the graphing of the solutions can be rather difficult. So we need techniques involving algebra to determine the solution exactly. And so because these techniques use algebra, they are also called algebraic methods. And so we'll be talking about primarily two methods. The first one is the method of substitution. And so let's look at the first example here. The idea of substitution is really pretty simple. Let's say we have this system of equation x plus y equals 6 and y equals x plus 2. Two equations and two variables. But we are given explicitly what y is in terms of x. So think about replacing this expression of y with x plus 2. Obviously it's the same. We have an equal symbol here. So then equation number 1 becomes x plus, and I'm going to put this in parentheses just to be very explicit, x plus 2, because that is what y is, equals 6. So what happens here now is we simplified the problem. Instead of dealing with two equations and two variables, now we have one equation and one variable. And of course, we have done that many, many times before. And so we just combine like terms. So 2x plus 2 equals 6. So we solve for x. So then x equals 2. So we have one of the variables determined. And now to find out what y is, we can use the second equation, y equals x plus 2. So y equals x plus 2. X plus 2, and since x equals 2, we can write this as y equals 2 plus 2, and that's equal to 4. So then the ordered pair 2, 4 is our solution to the given system of equations. So that's how substitution works in principle. Of course, it isn't always that straightforward and always that easy, but that's the general idea. And so we look at several examples that employ the same technique though. So the details may be different, but the idea is the same. Let's look at example number 2 and see if we can use the same approach. So the first equation says y equals 7 minus x, and the second equation says 2x minus y equals 8. So again, here y is given in terms of x, and here's a y. So all we need to do is substitute for y the expression 7 minus x. So therefore, from the second equation then, 2x minus, and so we need to be careful and use parentheses, because 7 minus x, that's what y is, equals 8. So be very careful when you have minus signs. Better use parentheses. Don't write 7 minus x. Because this then becomes 2x minus 7 plus x when we eliminate the parentheses equals 8. So that would be 3x equals 15. So x equals 5. So now that we know what x is, we can use that value and substitute that into the first equation. So y is equal to 7 minus x, and x is 5, so therefore y equals 2. And so then the solution to this system of equations is the ordered pair 5, 2. Let's look at the next exercise. 2y plus x equals 1 and y minus 2x equals 8. And so there's really not one example where y is given in terms of x or vice versa. But when we look at the second equation, by adding 2x to both sides, the second equation becomes y equals 2x plus 8. Why would I do that? Because now I can substitute for y into the first equation. Okay, so now from the first equation, we get 2 times y, and what is y? Well, y is 2x plus 8. 2x plus 8. Plus x equals 1. So then we use the distributive property, that becomes 4x plus 16 plus x equals 1. So we have 5x equals minus 15. So x equals negative 3. Okay. So I hope that you can solve an equation like this without too many problems. By now you should really know how to do that. And so if solving an equation like this is a problem for you for x, then please do enough that you can do this quickly. And so now we can use the any one of the equations to determine what y is. So let's use this one here. Y equals 2x, and x is equal to negative 3 plus 8. So that means minus 6 plus 8 equals 2. So x equals minus 3 and y equals 2. So the ordered pair -3, 2 is the solution of this system of equations. For the first three exercises, everything worked out well. We got one solution, one value for x, one value for y. But let's look at some special cases. When solving a system of two linear equations and two variables, if a false equation is obtained, then the system has no solution. And if a true equation is obtained, then the system has an infinite number of solutions. So let's look at some of those special cases. Let's look at this exercise number 5, solve using substitution. So there's nothing that's specific about it, which we don't have this, y equals something or x equals something. So, but when we look at the first equation, we subtract 2x from both sides. So then that equation becomes y equals minus 2x plus 3. And with that information now, y equals minus 2x plus 3, we substitute that into the second equation. So now we have in the second equation minus 2x plus 3 by substituting for y. Let me just put that in parentheses to make it more obvious. Plus 2x, that this one here, equals minus 4. So that's from the second equation, and we substitute minus 2x plus 3 for y. So we can drop the parentheses, and so we get minus 2x plus 3 plus 2x equals negative 4. Now, minus 2x plus 2x is 0, so we eventually have 3 equals negative 4, and that, of course, is a false statement. It's a false equation. And from the previous discussion we had a moment ago, that says there's no solution. No solution. So when we have a false equation, or some people call it a contradiction, then there's no solution to this for this system of equations. Okay? So that can happen. Now let's look at another exercise, exercise number 6. And so we are supposed to solve that by substitution also. And so let's just look at that. And we look at the first equation and the second equation. And let's say we add 3y onto both sides in the second equation. So then x equals 3y plus 1. Okay? And so we can substitute this, this value for x into the second equation. So let's do that. So we get from the second equation, we get 6y minus 2 times, and now comes x, and x is 3y plus 1. 3y plus 1 equals negative 2. That is negative 2 here. So we have 6y minus, using the distributive property here, minus 6y, and minus 2 times 1 is minus 2, equals negative 2. When we combine like terms, on the left side, we notice that 6y minus 6y is 0, and of course minus 2 equals negative 2. And that is a true statement. That's a true equation. That indicates an infinite number or infinitely many solutions exist to this system of equation. So infinitely many solutions. Infinitely many solutions. Okay, so that's for that example. And if you do more exercises for homework or out of the book, I'd highly recommend it, so you get a feel for what it's like to solve systems of equations by substitution. Okay, let's look at an example. It says here the top floor of the John Hancock building in Chicago is in the shape of a rectangle. The also refers to previous exercise. Its perimeter is 520 feet. The width is 60 feet less than the length. Find the length and the width of that rectangle that has a perimeter of 520 feet. So in a case like that, it's really a good idea to start with a little drawing to make sense of what we're looking at here. Let's finish the section with an applied problem solving for two equations. And so here the architecture problem says the top floor of the John Hancock building is in the shape of a rectangle. Its perimeter is 520 feet. The width is 60 feet less than the length. Find the length and the width. So here's a rectangle, typical rectangle. And so we know the perimeter, P, is equal to 2 times the length plus 2 times the width. And you can look up this formula also in the back of the book. Now we know that the perimeter is given to be 520 feet. Now we also told that the width is 60 feet less than the length. So we have the equation W equals the length minus 60 feet. So how can we solve this system of equations by substitution? Well, we're given W in terms of the length, so we can substitute for W in the first equation. So that means we have 2L plus 2 times, again, now for W, we replace it with L minus 60, because that's what W is, all being equal to 520. Then we use our distributive property to eliminate the parentheses, so we get 2L plus 2 times L, or 2L, and 2 times minus 60 is minus 120, and this is equal to 520. When we combine like terms, we get 4L, and when we add 120 to both sides, we get 640. And so that means that L is equal to 160 feet. Now for the width, we know that the width is L minus 60. So the width is equal to L minus 60, or 160 minus 60. So L is equal to W rather is equal to L minus 60, and so that would be equal to 160 minus 60, so then W equals 100 feet. So in other words, the length equals 160 feet, and the width equals 100 feet. This concludes section 3.2.